in the first example, we're going to find the resistor Rx. What we know from the problem is the current flows through this resistor and also the power absorbed by this resistor. From the power calculation, we know that power is equal to the voltage times the current flow of this resistor. We also know Ohm's law tells us that the voltage on the two terminals of this resistor that is equal to the resistance times I. By combining these two together, we can find the power by using I squared times R. So in this problem, we already know that the current flows through this resistor that is 2 milliamp, and the power is given 20 milliwatts. So we'll be able to find the resistance Rx. Rx is equal to P divided by I squared. We have 20 milliwatts, 10 to the power of -3, and the current is 2 milliamp. 20 divided by 4, that is 5 kilo ohm. Let's look at the second example to find the current I1, I2, and I3 in the network. So I1 is connected to node B and also this node A. If we look at this node A, there's only one unknown, which is I1. So we can apply KCL at node A. Let's count the algebraic summation of the current that goes into node A is equal to 0. So we have I1 plus 5, the current goes in there, minus 2 plus 4 minus 8, that is equal to 0. So we can solve for I1 is equal to 1 milliamp. If we look at the node B, there is only one unknown current I2, so we can apply KCL at the node B. Then write the nodal equation over there. We have, if we count the current leaving the node as positive, so we have I2 leaving the node minus 3 plus 6 plus I1 is equal to 0. So we can solve for I2, which is equal to 3 plus 1, 4, so that is a -4 milliamp. Next, to find I3, we need to apply KCL at this node C. So we'll apply KCL at the node C, we'll write a nodal equation. If we count all the current leaving the node adds up to 0, so we will have I3 leaving plus 4 leaving minus I2 minus 8, that is equal to 0. Then we'll be able to find I3 is equal to 0 milliamp. Next example, I'm going to find I0 and I1 in the circuit. So I0 is over here, I1 is over there. To find a current I1, by looking at this node, we need to find I0. To find I0 connected to this node, we need the current in this branch as well. So we don't know the current in this branch. So we can define the current in this branch first. Let's call this current I2. Let's define the nodes. Call this node A, this will be our node B, and this will be our node C. And this will be our first method. Method 1, apply KCL at a node A. We have the current leaving the node, which is I2, that is equal to the summation of the current that goes into the node. I2 that is equal to 2 plus 4 is equal to 6 milliamp. Next step to apply KCL at a node B. Let's use the current leaving the node as up to 0. So that is a I0 plus 3 minus I2 that is equal to 0. So we'll be able to find I0 is equal to 3 milliamp. Then we can apply KCL at the node C. So the current leaving the node I1 plus the current leaving the node 5 milliamp in this branch over here, and minus the current that goes into the node IO is equal to 0. So we can find I1 is equal to negative 2 milliamp. The second method, we can define part of a circuit as a node so that we can simplify the calculation. For example, if we define this part of a circuit as a one giant node, let's call this node D. If we apply the KCL at a node D, we notice that there are 4 branches connected to this node. IO is a 3 milliamp, 2 milliamp, and a 4 milliamp. So there will be only one unknown. So if we use the summation of the current leaving the nodes adds up to 0, we have a IO plus 3 leaving minus 2 minus 4 is equal to 0. Then we can find an IO is equal to 3 milliamp. So now you can see that actually we select part of the circuit to be one giant node to ensure there is only one unknown in the equation, so which greatly simplify the calculation. So we can do the same thing to find I1. So by looking at I1 is connected to this node and that node, if we define this part of the circuit as our node, say this is my node E. We define this part of the circuit to be the giant node E. Now we can apply KCL at this node E. So apply KCL at a node E. If we count all the current goes into the node as a positive, so we have I1 plus 5 minus 2 minus 4 plus 3 is equal to 0. Now we can find I1 as negative 2 milliamp. In this problem, we're going to find a VBE and a VDA. So this is BE, VDA. So I'm going to find out the loop that will include a VBE so that I can use KVL to find a VBE. So I'm going to define a loop like this. VBE. So this is my first loop. Let's give it a name, say loop 1. Apply KVL to loop 1. We're following the direction of loop 1 to write the KVL equation. Have the voltage drop VBE, first BE, and there's another voltage drop of 4, so plus 4, and there's an increase of 24, so we minus 24, because we are looking for voltage drop. So there is another voltage drop of 12, which is equal to 0. So we can find a VBE is equal to 8 volts. And similarly, we can find a VDA. So we need to define the loop VDA. So let's define VDA, DA. So say I'm going to use this as my loop. So I'm going to give it a name, say loop 2. Apply KVL to loop 2. We have voltage drop of VDA. And then there is a voltage drop of 8 plus 8, followed by another voltage increase minus 6. Then there is another voltage drop of 4 plus 4, that is equal to 0. So we can find a VDA. VDA is equal to negative 6 volts. Let's look at the next problem. In this example, we're going to find a Vx and a Vy. Vx is over here, Vy is over here. So we need to define a loop. Hopefully we can find a loop that only have one unknown so that we can solve the equation easily. To find a Vx, we can define a loop like that. Vx goes to this 4 volts and a 6 volts power supplies and come back to form a loop. So let's do it. I'm going to define this is my loop. Give it a name of loop 1. So we'll say apply KVL to loop 1. We can write the loop equation by adding the voltage drop that is equal to 0. So we have voltage drop Vx minus 4. Then this is an increase of 6, so that is a minus 6. We have an increase of 12, minus 12. That is equal to 0. So we can find a Vx that way. So Vx is equal to 22 volts. And similarly, we can find Vy. We can define the loop like that so that we only have one unknown, Vy. So we define this loop, we call it loop 2. Let's apply KVL to loop 2, then we write a loop equation Vy, the first of all. So let me change the direction of the loop. Following this direction, we have voltage drop of Vy, now another drop of 6, then there is an increase of 12 minus 12, that is equal to 0. So we'll be able to find Vy that is equal to 6 volts. So this is the first method, call this method 1. Method 2, we will use the definition of a voltage to do the problem. For example, Vx, that is the voltage drop from this end to that end, we can find that by following any branches to find Vx. The Vx is equal to the voltage drop 12 plus 6 plus 4. That gives us 22 volts by using the definition. So we'll have a Vx is a voltage drop from this node to that node. So we can follow this path. 12 voltage drop, then 6, then plus 4. So that will give us 22 volts. And similarly, we can find a Vy. Vy is the voltage difference between this node and that node. We can follow this path. So that is 12 volts minus 6 volts. That is equal to 6 volts. So in the exams, as long as you tell me which method that you use, so both of the two methods are good.